All right, so let's get this webinar started. Hi, everyone. My name is Neerav, and I'm a sales and application engineer at Luceda Photonics. Today, I'll be giving a talk on a data-driven approach to analyze the thermal crosstalk in a PIC switch network. So here's the outline of my presentation. First, I shall give a quick introduction to my company, Luceda Photonics. I shall then give an overview of switching networks and talk about how the design of such circuits is enabled using our software. Then I shall dive into the main content of this talk, which is the data-driven variability analysis flow, which enables different kinds of studies. I apply it to calculate the thermal crosstalk in a switching network, and then I shall conclude my talk. We shall have a question and answer session at the end where I shall answer your questions. You can ask your questions by unmuting yourself or by typing them into the meeting chat. All right. So Luceda Photonics was founded in 2014 out of the Belgian photonics ecosystem. It was created with the long-term goal of enabling photonics IC designers to enjoy the same first-time right experience as electronics IC designers. Our mission is to accelerate the time to market of PIC design teams by helping them set up a flexible and efficient design flow. We have a presence around the world, including a branch office in Shanghai. We have a partnership with Spark Photonics to best serve the photonics engineers in North America. By using Luceda, you have access to a team of photonics experts who can help you achieve your goals. The way we aim to achieve our goal is through the Luceda Photonics design platform, which is a comprehensive Python-based design platform that leverages the flexibility and automation of code to take you from component design to circuit design and simulation and design validation. All of the features in our software help reduce design errors and improve time to market. This slide features the Luceda Photonics design platform. It consists of our core product, Luceda IPKISS, which enables all of the core features of photonic design, from schematic capture to circuit layout and simulation to component layout and simulation and design verification. You can access PDKs across many different material platforms from different foundries and also get design kits for assembly and testing. We also offer specialized modules such as AWG Designer, a toolbox to help you synthesize arrayed waveguide grating circuits from a specification perspective. We also offer IP Manager to help you validate and test your IP libraries. We also released a new module last year called Circuit Analyzer, which helps you to study the impact of fabrication variability on the performance and yield of your circuit. Today, we shall be using this tool to do the thermal crosstalk analysis. Besides this, we also offer links to third-party tools, including several device simulation tools like Lumerical FTTD, CST Studio, and Tidy3D. We link with Siemens Eledit and also to OptiSystem, and we support a link to a DRC checking tool called Checkmate DRC. All right. With that out of the way, I shall give a brief overview of optical switching networks and introduce the problem we are trying to solve. So optical links facilitate ultra-high bandwidth communication because you have a high-frequency carrier wave and the ability to transmit multiple channels over the same medium, which is typically fiber. When multiple endpoints use optical links, you would need a switching network to coordinate input data channel to the correct output. A few of the application domains of optical switching networks are listed here. The most obvious one is telecommunications, where they can be used in mobile networks. But you can also use switching networks to coordinate data packets between different computing nodes in the data center and even extend it to intra-chip communication. AI models, which need to be trained on massive data sets, could also benefit from a higher data transfer rate between computing cores. You can apply switching circuits in quantum computers, where they can be used to initialize the spin of a qubit and entangle single photons. And deep learning using photonic neural networks can also benefit from switching matrices. Switching networks are usually based on cascading multiple unit cells, typically comprised of 2x2 switching blocks in different schemes to achieve n-cross-n routing. Individual switching action is usually achieved by leveraging the electro-optic or thermo-optic effects in different ways. You would need to optimize the bandwidth, minimize the insertion loss, the crosstalk, and so on. These 2x2 switching blocks can be connected in different schemes to achieve non-blocking switching in N-cross-N ports, like the Benish, the Pylos, Banyan, and so on. You want to evaluate these architectures with the same criteria. You want to look at the loss, the power consumption, the footprint, and so on. You also want to do a systematic comparison where the choice of architecture and the unit 2x2 cells are evaluated rigorously. And you also want to know whether a switch can scale up. Practical effects due to heat constrain how much such circuits can scale up. While one can optimize individual components, the system level behavior would entail crosstalk effects which are difficult to model. For example, if one actuates a 2x2 switch, the heat impacting a waveguide is not limited to the zone around which the heater is drawn, but the heat spreads out spatially, which causes a different phase shift over the entire unit cell. For a single switch, one can tune the voltage to get the best extinction. However, in a wider switching network, the heat also leaks to nearby components and switches. This leads to thermal crosstalk in a wider network. The heat from one heater can impact the performance of an adjacent switch, and we need to figure out what design changes we can make to keep these switches tolerant to thermal crosstalk. Of course, a quick fix would be to use trench isolation layers to isolate them, but this would impact the speed and also the size of the chip. Ultimately, you want a parametric design and analysis framework to evaluate how far you can scale your switch radix. So let's see how the design of such a circuit benefits from our framework. As I mentioned earlier, you can have different switch architectures, and you want to evaluate the properties such as insertion losses, crosstalk, and footprint properly. What you want from your design tool is the ability to adjust the circuit layout and simulation with ease. You want to iterate over multiple designs easily to study the effect of different changes to your layout. Ideally, with a parametric approach, you would have to just punch in a number at the end, and you'd get a circuit with n inputs with no manual effort from a designer. Circuit simulation must be powerful, where you want to be absolutely sure that what is being simulated is what is drawn in layout. You also want to analyze all of your output spectra the same way so that there are apples to apples comparisons. So design, simulation, and analysis. It's possible to do parts individually in different softwares, which can get tedious. Iterating over different designs and debugging them over different platforms becomes very cumbersome. And we offer a solution where you can do all of it on our unified platform. From a bird's eye view, a user is given 3 axes of control. Layout, where you have control over the components, the connections, and placement, which is all defined in code. You can make a parametric circuit to freely change it as you please, either within the 2x2 unit cell or within the wider switching network. Changes to the circuit layout will be reflected in the simulation. It is possible to do frequency and time domain simulations in IPKISS. You can apply any input signal you want and probe any legitimate port in your circuit. The user is given control over what inputs they can apply or what ports can be probed without messing with the layout. Finally, you can plug your circuit into a test bench and evaluate its properties with no regards for how it's implemented. So with these 3 axes of control, there's no back and forth between different softwares. It's all seamless. Defining an MZI 2x2 switch circuit in our platform, IPKISS, is pretty straightforward. You have to specify the individual instances inside it, which are the directional couplers and the heater. The pseudocode shown here on the left is very similar to the actual code you would use to define an MZI, with some minor syntactical jargon removed for clarity. You can automatically connect the heater to the directional coupler using Manhattan connections, which are routed at right angles. And you can also choose how the waveguides are routed. This MZI can be reconfigured with different offsets and heater lengths by just changing a variable. I created a 4x4 circuit in the Benish architecture by cascading multiple 2x2 blocks. I added in a waveguide crossing component where the waveguides intersect. Creation of a 4x4 circuit is very similar to that of a 2x2 block, where I just specify place the first 2x2 switch at the origin, place the second switch at a certain offset away from it, connect them using a bent waveguide, and so on. The schematic capture tool allows you to visualize large functional circuit blocks without being overloaded with information about the implementation of every subcircuit. Here, you can see how 2x2 blocks must be connected together with crossings in between to form the 4x4 Benesch circuit. The beauty of using IPKISS and parametric design is that the 2x2 or the crossing can be replaced with ease in code, and this will be reflected in the circuit simulation. Speaking of which, simulation does not require any additional effort from a designer. One would just need to make an object of the circuit model subclass and call a method to calculate the S matrix. It reads the S matrices of the directional couplers, the waveguides in the heater, and automatically calculates the response of the circuit while also accounting for voltages. It adjusts with any layout-related changes to the unit switch, and the same principle applies even for a more complex circuit. You can see here that for a 2x2 switch implemented using our example PDK, SciFab, one can see switching action when a voltage is applied to the heater. You can also visualize the wavelength-dependent response of the circuit in the cross and bar states by applying different voltages. One can also use a module called Tracer to track the flow of light across your circuit. This plot is interactive and you can inject light wherever you want. This allows the users to debug more complicated circuits. You can hover your mouse over different nodes and analyze the amount of light leaking into adjacent ports and waveguides. The intensity of light is coded by the color of the lines. All right, so now that I've covered how IPKISS can help with the design of the initial layout and simulation of a switch, I shall now talk about the variability analysis toolbox called Circuit Analyzer. Photonic integrated circuits generally have varying physical parameters as a consequence of imperfect fabrication. Light is incredibly sensitive to small variations, which cumulatively introduce phase changes to the guided mode over the circuit. These imperfections could be correlated and spread across the wafer and chip. One can analyze the impact of these variations using our circuit analyzer toolbox by using various types of analyses like corner analyses, Monte Carlo simulations, and wafer map simulations. Suppose I have a circuit like the Benesch switch, and I have a known thickness and width variation limit. To analyze the worst and best case scenarios, one can do a corner simulation. One would just need to specify the parameter variations like the thickness and waveguide width, minima and maxima, and one can get the simulated simulation corners. The parameters can also be varied spatially, and the circuit can be sampled at multiple positions such that the impact of spatial variability can be considered. Such a calculation can be used for wafer scale analyses. The yield of circuit designs can be calculated given a foundry's process parameters. The spatial variation could be thickness, width, or any combination of different parameters. I will be using the spatial variation analysis in conjunction with a thermal profile to calculate the thermal crosstalk in such circuits. So now that I've introduced what our toolbox can do, let's talk about how to actually do variability simulation. So setting it up is quite easy. One would need to introduce two files. The first file describes which parameters vary and what is the limit of the variation and points to a relevant mutation method. It is defined in the form of a YAML file, which is easy to read, as you can see on the right. In this example, I specify for a waveguide, the parameters which vary are the thickness and the width, and that the thickness varies between plus or minus 4 nanometers, and the width varies between plus or minus 0.5 microns. The second file describes the S matrix mutations for specific components, or in other words, how does the S matrix get modified as a function how does an S matrix get modified with respect to a certain parameter? This separation is useful because you mention the variation limits in one file and describe the impact of the variation in another. The mutation of the S matrix can be defined in two ways. The first is an analytical approach where the terms of the compact model are directly modified. For example, I could adjust the effective index of a waveguide by a flat amount dependent on a spatially varying temperature. The second is a data-driven approach where the mutated S matrices are stored in files which are read and interpolated. To go into more detail, in a data-driven approach, you could gather information of S matrices for different performance corners. For example, you can have a crossing with different possible waveguide widths, say a minimum, a nominal, and a maximum. You can get an S matrix to define the performance at all of the corners, and this can be acquired through a measurement or an FDTD simulation. Our engine performs an interpolation and creates a compact model which can be used for our variability simulations. So it can estimate the performance of the crossing for any intermediate width between these limits. And this interpolation can take place over multiple parameters, not just one. To run a variability analysis, you would just need to set up the YAML file, the mutation methods, and make a simple call to the variability analysis method. You can check out what analyses you can run using this toolbox by looking at our website. There are benefits to using this approach. So you can easily change the configurations to identify critical components in your design. The configurations and the variability data can come from a foundry or be defined by the user. And finally, you need not modify the source code at all. You can isolate all of the extra code for circuit analyzer in a single folder. So to give a quick summary, you just need to specify a configuration file and the mutations of the S matrix of the desired components. The mutations could be analytical or data-driven. Then the config file is opened in a Python context manager, and a variability analysis method is run. All right, so I've gone over the circuit analyzer toolbox. Now let's see how we shall use this to analyze the thermal crosstalk in a switching network. I use the following tools for my analysis. IPKISS was used to define the layout of the components in the circuits and also used to simulate them. Numerical FDTD was used to extract the S parameters of the directional couplers and crossings at different temperatures. And Circuit Analyzer was used to interpolate the simulation results and was applied to run a spatially aware variability simulation. So let's see this in action and calculate the impact of self-heating in a 2x2 switch. First, we must inform Circuit Analyzer how it must treat the components at different temperatures. We have three distinct components in the 2x2, the directional coupler, the waveguide, and the heater. I assume the heated waveguide is a lumped element, which provides an overall phase shift for a given voltage. And this is normally a number which would be provided by a foundry if it's provided as a foundry component. So the variability of the other two components must be defined in the model mutation files. The waveguide's thermal performance change is modeled using the analytical approach. I use this simple equation where the effective index is just increased by the thermo-optic coefficient multiplied by a change in temperature. The directional coupler's variability is calculated by using the data-driven approach. So the 3D model is exported to numerical FDTD to perform simulations. The indices of the core are modified to indicate the impact of temperature change. And the simulated results are shown on the right, where at a higher temperature, say at a maximum of 50 Kelvin change, the 3 dB wavelength increases by a couple of nanometers. So let's have a look at the Python project I made for this and look at what the code structure actually looks like. So go here. I have a design library which contains all of my components and circuits for this project. So I have a folder for the components, which includes the directional coupler and all of the information regarding the layout and how it is simulated in numerical, and the S matrix data at 0 and 50 Kelvin, or rather at nominal temperature and a 50-degree higher temperature. And the same applies for the crossing as well. All of the variability related information is confined to the folder called variability_information, where I have a YAML file, which specifies which components can vary, and what are the limits of variation. So in this case, I specified that there's a global parameter called T for temperature, which varies between 0 to 50 plus 50 Kelvin. Rather, it's more like a change in temperature, but I hope the point is clear. I mentioned that there's a waveguide whose effective index can change, and the mutation is specified in a method called waveguide underscore parameters under the models.py file. Similarly, I have a directional coupler whose S matrix depends on the temperature, and a similar component for the crossing as well. So within the models.py file, you can see the code to modify the compact model. In this case, I have a fixed thermo-optic coefficient, which I multiply with the varying parameter and just add it to the fitting coefficients. So this provides a flat rise in the effective index of the waveguide. Now, for the directional coupler, I won't go too much into detail to explain every single line of code, but basically it reads the S matrix data at different temperatures and does an interpolation. However, I add a modification to the compact model, which is that I enforce a fixed phase relationship between the output phase between the two arms of the directional couplers. And this is only done to avoid phase unwrapping related inconsistencies in the simulation. But yeah. All right. So I have this project structure. So let's see how we can run a simulation to calculate the self-heating in a 2x2 switch. So the idea is pretty straightforward. I first read the cross and bar voltages, and I initialize my P cell or my 2x2 switch. I calculate a thermal profile and I visualize it, or rather I superimpose the thermal profile on top of my switch circuit. Then I open a context manager with my YAML file, and I run a wafer map sweep and do the simulation. So this is first the circuit which is visualized. You can see over here that I have a 2x2 switch with a thermal profile superimposed over the layout. The temperature of the circuit is sampled at every red dot indicated on this image. So you can see that the directional couplers and the heater are sampled at the middle, whereas the waveguide is sampled every 2 microns. And now when I close this, it's going to run the wafer map simulation, and you can see what it does is it plots the transmission to the cross port for the nominal case and for the case with the thermal effects included. So to give a little bit more context, this is a 2x2 switch which is supposed to operate in the bar state, which means that any light from input 1 must go to output 1. That means that almost no light should enter into output 2. And in the nominal case, that is more or less true. You have minus 70 dB going into output 2. But when you account for the self-heating effect, you can see that the crosstalk is much, much higher. It's up to minus 14 dB. So this is how Circuit Analyzer can help you find the impact of self-heating in a 2x2 switch. Going back into the presentation, and maybe to give a bit more context about the thermal profile, because I create a non-physical temperature profile for this example. It's not based on real physics, although I did try to make it as accurate as possible. And you can replace this profile with your own one, which is based on real heat simulations or thermal profiles. At the end of the day, you would need a 2D map of temperatures over the circuit. I detect the heater components and find the ones which have a positive voltage bias and superimpose a profile over the heater. So yeah, I've already shown you that the crosstalk increases a lot when you have self-heating. So how do you mitigate this? One way to mitigate this is to increase the spacing between the arms. So you can isolate the two arms. Or you could apply a Python-based workflow to optimize the voltage and achieve a much lower crosstalk. In this case, I make the peak temperature of my profile vary proportionally to the applied voltage. And I tune it such that the phase shift within the heater is compensated by the additional phase shifts of the waveguide to the left and right. So essentially, if it would follow the relation shown on the right, and you can achieve a really low crosstalk even with self-heating. Okay, so let's consider a wider switching network like a 4x4. Now, thermal profiles of individual 2x2s can influence each other, and this results in an increased crosstalk in output channels. So you can play with a lot of parameters to optimize a higher radix switch. We have many dependent variables to judge the performance. So we have the transmission through the output ports, the crosstalk at each output port, and the transmission port pairs. Now, the thing is, at a certain point, the crosstalk becomes so bad that it's possible for one input channel to be routed to a completely different output channel. And this is something that we want to avoid. So for those three dependent variables, we have different things we can tune in the design. Assuming we freeze the design of the crossings and the directional couplers, you can change the height of the MZI and the spacing between the 2x2 switches, and also both in the vertical and in the horizontal dimensions. In this webinar, I vary the height of the MZI and the vertical spacing, but leave the horizontal spacing as constant. Another thing that will affect the evaluation is the bias state. So you'd have different insertion losses and crosstalks and routings for different combinations of heaters being activated. To evaluate this network, we do a design sweep over 3 different dimensions. So the height, the spacing, and the bias state. Out of all of the permutations of this switching network, I choose the ones where the fewest heaters are actuated at any point of time to achieve the 24 possible input and output combinations. I use the optimized voltages for each 2x2 switch to evaluate the worst case crosstalk and insertion loss. And I also detect port flips. So this ensures that the switch circuit behaves like it is supposed to, even in the worst case scenario. And we'll find which design configurations fail. So I ran a sweep and plot the worst case performance. The x-axis depicts the height of the MZI, and the y-axis depicts the spacing between the switches. The two plots show the worst case crosstalk amongst all of the bias states and the worst case insertion loss. If in any one of the biasing states a port flip occurs, that design is marked with a cross. Whereas if the design routes the signal correctly to the intended port in every situation, then it's marked with a green check. I see that regardless of the height of the MZI, the trends are pretty clear. For very short spacings, the crosstalk is very high and one can encounter port flips. And as the vertical spacing between the switches is increased beyond 20 or 30 microns, the crosstalk pretty much saturates. This implies that isolating different layers of the switch is more important and that self-heating in a 2x2 can be compensated by applying a proper bias voltage. This kind of analysis can be extended very easily. So for example, if I set an area limit for my chip, I can see over this contour which designs are permitted. If my area is larger than, for example, 0.5 millimeters squared, then it is hidden by a white mask. You can also plot an area versus crosstalk to see how well your design can scale. So to conclude, I demonstrated an integrated layout simulation flow, which makes parametric switch design easy. Nominal models can be readily obtained from foundries and simulations and be plugged into circuit level simulations. Circuit Analyzer enables variability analyses of circuits to improve yield. One can do corner analyses, Monte Carlo analyses, location-aware, spatially correlated variable analyses, and data-driven workflows are supported, which incorporate simulations and measurement data into the variability analyses, as I demonstrated here with the directional couplers and the crossing simulations. The layout of a workflow was applied to analyze the thermal crosstalk in a simple 4x4 switch, and the circuit parameters were tuned to identify an acceptable design. So just to reiterate, what I showed in this webinar was based on a fictional foundry process using a hypothetical temperature profile. But you can use a PDK provided heater from a real PDK and perform your own 2x2 switch design using that. And the temperature profile can be simulated using a thermal solving engine. As long as you get a 2D temperature map, it can be used with Circuit Analyzer. For further possibilities using our workflow, we have a few more ideas. For example, I optimize the voltage for just a 2x2 switch, but the same thing can be done for a wider switching network to see what can be achieved. You can use the same workflow to analyze a high radix switch like that of an 8x8 Benish switch. You could add trench layers around the 2x2 switches to reduce the crosstalk, or you could also investigate other architectures like the Spank-Benish architecture. That concludes my talk. You can find out more about our products by visiting our website or by contacting me. I would be happy to send over the project which I implemented for this talk upon request and provide a week-long trial of Circuit Analyzer licenses so that you can play around with it. I would be happy to answer your questions now.
Hi, thanks for the talk. Can you also include imbalance in the directional couplers?
Yes, you can. I did not do it in this particular scenario, but indeed, you can add as many varying parameters as you want into the analysis. In this particular case, I restricted it just to temperature, but it can be even thickness and width, which would introduce imbalances.
Okay, thank you. I have a second question. Has the circuit analyzer been proven in the field?
That's a great question. So, indeed, a couple of months ago, we collaborated with Alcyon Photonics, and we released a white paper where they validated their designs through both simulations using Circuit Analyzer and through measurement, and showed that their designs have a higher, uh, 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 a better yield. Let's see. Yeah.
All right, thank you very much.
I think they're in the call even. I see Eduardo.
Thank you.
Let me stop sharing my screen for a bit to see if there's any questions in the chat. So we have a question called how can we have a question how can we join the Luceda Academy? So Luceda Academy is our tutorial is our set of tutorials which is hosted on our website, and it's also distributed with our software. So if you want access to it, yeah, if you contact us, we can give you a free trial and you can have access to all of the Python scripts. But you can also look at everything that we have in offer by looking at the website. I shall type the link in the chat if that makes it easier for you. Okay, so there's another question which says, I was wondering about the trench isolation for further improvement. What should we consider when we want to use trenches? So the thing is indeed that trenches introduce air gaps around the heaters, which let's say prevents the leakage of heat to nearby switches. The consideration, and this will reduce the speed of your switching if that is a concern for you, and it will also introduce, let's say, constraints on the size of your chip, because I believe that there's also DRC specifications on how close trenches can be placed. So using this type of analysis, you can actually see how close can you get your switches and get away without using trenches. And another consideration when using trenches is that the heat can leak in unexpected directions, which is also something you'd have to consider by using a thermal simulation. We have another question. To generate the 2D temperature map that I provide to CA, did I use the link to Lumerical? No, I did not. So I generated a thermal profile based on an analytical model which I wrote myself. It's not based on a physical simulation. So I also want to thank you, Eduardo, for mentioning that circuit analyzer is a useful tool. We also really enjoyed collaborating with you for the white paper. Okay, if there is no other question, I think we can stop the webinar. All right. Thank you all for attending. Of course, if you have any questions which you wanted to ask but were unable to during this webinar, you can always write an email to me or reach out to us via our contact page, and we'll be happy to get back to you. Thank you.
Thank you.
Thank you. Bye.